In 1925, a 24-year-old working through glass photographic plates at Harvard found the answer to the oldest question anyone had ever asked about the night sky: what the stars are made of, what everything is made of. She was right, to within a rounding error of the figure we still use 100 years later. And the most powerful astronomer in America told her, in writing, that her answer was clearly impossible. So she left every calculation standing on the page, and underneath it she wrote that the most important part of her own discovery was almost certainly not real. Because being right, by itself, was never going to be enough. Her name was Cecilia Payne, and you have probably never heard it. You learned that the stars are made of hydrogen. You were never told who found that out, or what it cost her, or that a man published the same finding 4 years later and wore the credit for 50. Tonight, we walk back through all of it. The thin band of color that cracked open a problem the experts had called unanswerable. The equation out of colonial India that revealed why starlight had been lying to everyone reading it. The letter that branded the truth impossible. And the part that should sit badly with you, which is what her numbers quietly say about the matter you are built from. Settle in and subscribe or join if you have not, because this one only gets darker the further down you follow it. And by the end you will understand why you are made almost entirely of the part of the universe that barely registers in the measurement. If you want the wider trail, the deep time, and the other buried discoveries cut from the same cloth, that is what the Patreon is for. Let us start where it started. The most important sentence ever written about the stars is a sentence that the woman who wrote it had just been talked out of believing. She was 25 years old. It was the autumn of 1925, and she was working in a building at Harvard that women were barely permitted to enter, going through a collection of photographic glass plates that held the recorded light of hundreds of thousands of stars. And in the middle of doing something no human being had ever done, which was to calculate what the universe is actually made of. She arrived at an answer so strange that the most powerful astronomer in America had already written to tell her, in almost exactly this word, that it was impossible. So she did something I have never been able to get out of my head since the first time I read her thesis. She kept the answer, every number, every calculation, every result. She left all of it standing on the page. And then she added one sentence near the end, stating that the most important part of her own discovery was almost certainly not real. She was right. That is the part you have to sit with before anything else. Not almost right. Not right in spirit. She was right in the way that gets poured into the foundation of an entire science and never moved again. 100 years later, the number she worked out in that building is still, to within a rounding error, the number we use today. And she wrote, in her own hand, in her own doctoral thesis, that it was probably wrong, because a man with more power than her had told her it had to be. Her name was Cecilia Payne, and the thing she discovered, the thing she was pressured into disowning, is the answer to a question you have probably never bothered to ask, which is, what are the stars made of? And sitting underneath that question is a much larger one that she answered at the same time, almost by accident, which is, what is everything made of? You already have an answer in your head. Somewhere, everybody does. Think about what a star actually looks like to you. The sun, mostly. A furious, blinding, complicated object, powerful enough to run an entire planet's worth of weather and oceans and life. And there is a quiet assumption that comes attached to that image, which is that something that powerful, something that violent, has to be made of something substantial, heavy material, burning metal, the kind of dense, serious matter that could plausibly fuel a fire that size. It is not. A star is almost entirely the single lightest, simplest, most forgettable thing that exists in all of chemistry. Hydrogen, one proton, one electron, when it bothers to hold on to one. The first entry on the periodic table, the element so basic that it is barely an element at all. The Sun is roughly 3/4 hydrogen by mass. Almost all of the rest is helium, the second simplest thing there is. And everything else, every single other element, all 90 or so remaining entries on the periodic table added together, the carbon and the oxygen and the iron and the gold, and every atom that is not one of those first two, comes to somewhere between 1 and 2% of the Sun. A trace, a garnish, a contaminant. I want to plant something in your head right now, because we are going to come back to it later, and when we do it, it's going to feel considerably worse than it feels at this moment. Everything you would ever point to as interesting about the universe, every element that builds a planet or a rock or a tree or a brain, the entire chemistry of your body exists out there as a kind of impurity, a rounding error in a cosmos that is essentially two gases. The universe is hydrogen and helium. You are made of the part that barely shows up in the measurement. Hold that thought. We will earn it. Because here is what should already be bothering you. This is not an obscure fact. This is not a contested edge of physics that lives in some unread journal. This is the chemical composition of the observable universe. This is the answer to the most basic question you could ask about the night sky. And the woman who first proved it was talked into writing that she did not believe her own proof by the most respected astronomer in the country, who then, 4 years later, published the same conclusion himself, and spent the following several decades being credited with the discovery in the textbooks. You learned, if you learned anything, that we know the stars are made of hydrogen. You were never told the name of the person who found out, or what it cost her to find out, or what was done to her afterward to make sure her name was not the one attached to it. And nobody is talking about it. That is the file we are going to reopen. Not just the science, though the science is stranger than the clean version you half remember. The whole episode, because the way we came to know what the universe is made of is not a story of patient discovery building calmly toward truth. It is a story about a correct answer being found, being attacked by authority, being publicly disowned by the very person who found it, and then being quietly absorbed into the body of accepted knowledge with somebody else's name on it. And the answer in question is not minor. It is the composition of all the visible matter there is. To understand how strange that is, you have to understand what people believed before Cecilia Payne sat down with those plates. Because the wrong answer was not stupid. That is what makes it dangerous. The wrong answer was beautiful and elegant and supported by the best data of the age and endorsed by the smartest people alive. The wrong answer felt exactly like the truth. For most of human history, of course, the stars were not made of anything you could name, because the idea that they were made of the same kinds of stuff as the ground under your feet was itself radical. Aristotle had taught, and Europe had believed for the better part of 2,000 years, that the heavens were composed of a fifth element, a celestial substance, fundamentally different from the four earthly elements of earth: water, air, and fire. The sky was made of sky. The stars were made of star. Whatever the heavens were, they were not the same category of thing as a rock or a river. There was the world below the moon, which was corruptible and changeable and made of ordinary matter, and there was everything above the moon, which was perfect and eternal and made of something else entirely. And there was a hard philosophical reason to think we could never settle the question, which is that you cannot go there. You cannot take a sample of a star. The French philosopher Auguste Comte made this exact point in 1835, and he chose the composition of the stars specifically as his example of a thing that science would forever be unable to determine. He wrote that we would never, by any means, be able to study the chemical composition of the stars. He picked it because it seemed like the safest possible bet. The stars are unreachable. Their substance is hidden behind an unimaginable gulf of empty space. Of all the things a person in 1835 could be certain humanity would never know, surely the literal material of a distant sun was at the top of the list. He was wrong within a few decades, and he was wrong because of a thin band of color. Here is where it gets stranger than the version you remember. Because the tool that broke Comte's impossible problem wide open is the same tool that would, 70 years later, lead the entire field into the wrong answer about composition. The instrument that revealed the truth also manufactured the lie. The spectroscope. When you pass sunlight through a prism, you get a rainbow, which you know. What you may not know is that the rainbow is not smooth. Run it through a fine enough instrument, and the band of color is crossed by hundreds of thin, dark lines, narrow gaps where specific colors are missing. Those lines were first noticed in detail by a Bavarian optician named Joseph von Fraunhofer in the early 1800s, a man who had been orphaned, nearly killed when the glass works he was apprenticed in collapsed on top of him, and who would die at 39 of the heavy metal poisoning that came with the trade of making glass. He catalogued 574 of those dark lines in the solar spectrum without knowing what a single one of them was. He just knew they were there, in fixed positions every time, like a barcode printed across the sun's light. The meaning of the barcode came later, in 1859, from two men in Heidelberg, the physicist Gustav Kirchhoff and the chemist Robert Bunsen, the same Bunsen whose burner sits in every school chemistry lab. They figured out that each chemical element, when heated, glows in its own precise and unrepeatable set of colors, a fingerprint of bright lines unique to that element and no other. Sodium glows in one specific yellow. Hydrogen glows in its own particular reds and blue-greens. And crucially, the same element, when light passes through it while it is cooler, absorbs those exact same colors, punching the dark lines into the spectrum at precisely the wavelengths where it would otherwise have glowed. Which meant the dark lines in the sun's light were a signature. Each one corresponded to an element sitting in the sun's atmosphere, absorbing its own private colors out of the light streaming up from below. For the first time in history, you could point an instrument at a star, catch its light, spread it into a spectrum, read the dark lines, and name the elements that were present. Comte's unanswerable question had an answer after all, and the answer was written in a code that anyone with a good enough prism could begin to read. That should have been a clean triumph. And in one sense it was, because by the end of the 1800s, astronomers had identified dozens of familiar earthly elements in the sun. Sodium, iron, calcium, magnesium, hydrogen, all of them, their fingerprints unmistakable in the solar spectrum. The heavens were not made of some untouchable fifth element after all. The sun was made of the same stuff as the earth. The same chemistry, the same periodic table, the same elements you could hold in your hand in a laboratory. It was a profound and genuinely correct unification of the cosmos. The sky and the ground were made of the same kinds of atoms. But here is the trap, and the entire story turns on it, so I am going to be careful. Knowing which elements are present is not the same as knowing how much of each there is. The spectrum tells you that hydrogen is there, and that iron is there, because you can see both of their fingerprints. It does not, at least not in any obvious way, tell you whether there is a little iron and an ocean of hydrogen, or a lot of both, or the reverse. And the most natural assumption in the world, the one that almost everyone made, was that the strength of a line told you the amount of the element. A bold, dark, heavy line meant a lot of that element. A faint line meant a little. It is the obvious reading. It is also completely wrong, and being wrong about it would send the greatest astronomers of the early 20th century to a conclusion that was elegant, unanimous, and false. Because when you read the sun's spectrum that way, the lines of the metals, of iron and calcium and the heavier elements, are strong and dark and dramatic, and the lines of hydrogen, while present, do not dominate the way you would expect if the sun were mostly hydrogen. So the conclusion drew itself. The sun, like the earth, is a rich mixture of all the elements, with the metals well represented, just as they are in the rocks beneath your feet. The cosmos is uniform not just in its ingredients, but in its recipe. And the man who would make that idea rigorous, who would turn it from a general impression into a quantitative claim, backed by the best analysis available, was an American astronomer at Princeton named Henry Norris Russell. Remember that name. He is going to do something to Cecilia Payne that I still find difficult to describe charitably, even after reading The People Who Have Tried. But before Russell enters as the antagonist, you have to understand that he was not a fool and he was not a villain in the cartoon sense, and the wrong answer he defended was not lazy. It was the considered judgment of the field. And that is exactly why what happened next required someone from outside the field to see it. Someone who had not yet been trained into the assumption. Someone who, as it happens, had been told repeatedly that the field did not really want her in it at all. To see why the wrong answer was so hard to escape, you have to look at the single most persuasive piece of evidence behind it, because it is genuinely good evidence, and it fooled everyone, and the way it fooled everyone is a small masterpiece of how a correct observation can lead to a false conclusion. There was a man named Henry Rowland at Johns Hopkins who, in the 1880s and 90s, built the finest diffraction gratings in the world, ruling thousands of impossibly fine parallel lines into metal to spread light into spectra of a precision nobody had achieved before. With those gratings, he produced a map of the sun's spectrum so detailed that it remained the standard reference for decades. And he did something else. He ranked the strength of the lines, assigning each one an intensity, building a list of the elements in the sun, ordered roughly by how strongly they showed up. Iron at the top, blazing with thousands of lines. Calcium, sodium, magnesium, hydrogen, present but unspectacular, sitting well down the list, a handful of lines rather than thousands. Then, Henry Norris Russell did the thing that made the wrong answer feel like a law of nature. In 1914, he took Rowland's ranking of the elements in the sun and laid it next to the ranking of the elements in the Earth's crust, the abundances geologists had measured in ordinary rock. And the two lists matched. Not perfectly, but startlingly well. The elements that were abundant in the sun's spectrum were, by and large, the same elements that were abundant in the ground. Russell looked at that correlation and drew the conclusion that any reasonable person would have drawn. He wrote that the agreement was strong enough to confirm the view that if you took the Earth's crust and heated it to the temperature of the sun's atmosphere, it would produce very nearly the same spectrum. The sun and the Earth, he concluded, were made of the same stuff in very nearly the same proportions. Think about how convincing that is. It is not a guess. It is a measurement of the sun, matched against a measurement of the Earth, and the two independent measurements agree. That is the texture of real science. The moment when two unrelated lines of evidence converge on the same answer, and you feel the floor of certainty settle beneath you. The cosmos is uniform. The heavens are the ground, raised to a fever. It was elegant, it was supported, and it was endorsed by the man who would soon be called the Dean of American Astronomers, a title that was not ironic, because Russell genuinely was the central organizing intelligence of the entire American field, the man whose textbook taught the next generation, whose judgment could make or break a result, whose approval a young researcher needed the way a young researcher needs air. And it was wrong. The correlation was real, and the conclusion was false, and the gap between those two things is the whole story. But I am getting ahead of myself, because the person who would close that gap had not yet arrived in America. In 1914, when Russell published the comparison that locked the field into the iron sun, the woman who would unlock it was a 14-year-old girl in England who had not yet been allowed to study any real science at all. Cecilia Helena Payne was born on the 10th of May, 1900, in Wendover, a small town in the English county of Buckinghamshire. Her father, Edward, was a barrister and a historian and an accomplished musician, and he died when Cecilia was 4 years old, drowning, leaving her mother to raise 3 small children alone. Her mother, Emma, came from a distinguished Prussian intellectual family, and she was formidable, but the money and the attention in the household flowed, as it tended to in that era, toward the education of the son. Cecilia would later note, with the particular dryness she kept for these things, that her family was willing to spend on her brother's schooling in a way it was not willing to spend on hers. She was a child who taught herself, who memorized long stretches of poetry and Latin, who once, walking in the garden, became so convinced she had seen a meteor and so consumed by the desire to understand it that the memory stayed with her for the rest of her life as the moment something switched on. She fought her way into a good school and then, against considerable odds, into Newnham College at Cambridge in 1919 on a scholarship because there was no money otherwise. She went in intending to study botany. She did not stay a botanist for long, and the reason she changed is the kind of detail that the clean version of history files away as trivia, and that I think is actually the hinge of everything. In December of 1919, Arthur Eddington, one of the most important astrophysicists who has ever lived, gave a lecture at Cambridge about the expedition he had just returned from. Eddington had sailed to the island of Principe, off the coast of West Africa, to photograph a total solar eclipse. And what he had measured during those few minutes of darkness was the bending of starlight as it passed the sun, the deflection predicted by Einstein's brand new theory of general relativity. Eddington's measurement was the confirmation that made Einstein famous overnight, the thing that turned a German physicist into a global household name. And Cecilia Payne was in the audience. She wrote later that the effect on her was so total that it was close to a breakdown, that her entire picture of the world had been so shaken that she could barely function for days afterward, that she could reproduce the lecture in her mind almost word for word for the rest of her life. Most people in that room saw a brilliant talk. She saw the ceiling of her existence get torn off. She decided, more or less on the spot, that she was going to do this, that she was going to understand the physical universe, and she changed her course of study and pointed her entire life at the stars. And then she hit the wall that the whole story has been building toward, the wall that explains why the answer to what the universe is made of would have to come from someone with nothing to lose by getting it right. Cambridge, in 1923, would not grant her a degree, not because she had not earned it. She had completed all the work. The University of Cambridge simply did not award degrees to women, a policy it would not change until 1948, a quarter of a century later. She had done everything a man would have done to earn a degree from one of the greatest universities on earth, and at the end of it, she was handed nothing. Because of an accident of biology, that the institution had decided was disqualifying. So she left. She wrote to an American astronomer named Harlow Shapley, the director of the Harvard College Observatory, a man who was at that moment building one of the great research operations in the world, and she asked, in effect, for a way out. Shapley had recently set up a fellowship intended to bring talented women into research at Harvard, and Cecilia became, in the autumn of 1923, the second person to hold it. She crossed the Atlantic with almost no money and a stipend of around $500 a year, which even then was the salary of someone the institution did not take entirely seriously. And she walked into the Harvard College Observatory, and she found the thing that would let her answer Comte's impossible question. She found the plates. The Harvard College Observatory had been, for decades, the largest collection of photographed starlight in the world. Hundreds of thousands of glass photographic plates, each one a recording of the spectra of stars, an archive of cosmic light gathered patiently night after night and stored in case after case. It was an almost unimaginable trove of data, and it had been processed, measured, and catalogued largely by a group of women hired by the observatory to do the painstaking work of classification at a fraction of the wage a man would have been paid. They were called, in the language of the time, computers, because computing was a thing people did before it was a thing machines did, and the term was not flattering. The most brilliant of them, a woman named Annie Jump Cannon, had personally classified the spectra of several 100,000 stars and built the classification system astronomers still use today. The sequence of letters O, B, A, F, G, K, M that sort stars by the appearance of their spectra. Cannon could glance at a stellar spectrum and assign it a class in seconds, faster than anyone alive, with an accuracy that has barely been improved upon. She did it for decades, and she did it without the title or the pay or the standing of the men whose careers were built on the catalogue she produced. I am telling you about the computers, not as background color, but because Cecilia Payne walked into a building where the deepest understanding of stellar spectra resided in the hands of women who had been systematically denied recognition for it. That was the water she was swimming in. The institution was perfectly willing to use the labor and even the genius of women, as long as it did not have to call them scientists, or pay them like scientists, or put their names on the discoveries. Cannon had built the map. Payne was about to read what the map actually said, and the lesson of what happened to Cannon, the lesson hanging in the air of that observatory, was that doing the most important work in the building was no protection at all against being written out of the story. So here is what Cecilia Payne had in the autumn of 1924. She had the greatest archive of stellar spectra in the world. She had a classification system built by Cannon that sorted the stars by the appearance of their light without anyone fully understanding what the appearance meant. And she had something nobody at Harvard had quite put to use yet, which was a brand new piece of physics, fresh out of India and England, that for the first time made it possible to translate the appearance of a spectrum into the physical conditions that produced it. A piece of physics that was about to reveal that the entire field had been reading the spectra wrong. The metals looked abundant. The hydrogen looked modest. Everyone had taken that at face value, because why would the light lie? And the new physics was about to show, with brutal clarity, exactly why the light lies and exactly how much. The physics came from a man named Meghnad Saha, and his story is its own small indictment, because Saha was a brilliant Bengali physicist working under British colonial rule. The son of a small shopkeeper, a man who had been expelled from one school for joining a protest against a visiting British governor, and who did much of his most important work without the resources or the standing his European contemporaries took for granted. In 1920, Saha published an equation that, on its surface, was about something almost mundane. It described how a hot gas comes apart. Here is the idea, and it is the key that unlocks the entire universe. So I want to walk through it slowly rather than hand it to you as a finished result. When you heat a gas, the atoms in it are slamming into each other harder and harder, and the radiation pouring through it is more and more energetic. At some point, the collisions and the radiation get violent enough to start knocking electrons clean off the atoms. The atom loses an electron and becomes ionized, which is to say it becomes a charged particle missing a piece of itself. And a hydrogen atom that has lost its single electron is no longer a hydrogen atom in the ordinary sense. It is a bare proton. It cannot absorb the colors that hydrogen absorbs, because the thing that absorbs those colors is the electron jumping between energy levels, and the electron is gone. Saha's equation told you, precisely, given a temperature and a pressure, what fraction of the atoms of a given element would be ionized, and what fraction would still be hanging on to their electrons. And that is the hinge. Because the dark lines in a star's spectrum are not produced by all the atoms of an element, they are produced only by the atoms that are in exactly the right state to absorb that particular color. If the atoms are too cold, the electrons are sitting in the wrong energy level to absorb the line you are looking for. If the atoms are too hot, the electrons have been stripped away entirely, and there is nothing to do the absorbing. The strength of a line does not tell you how much of an element is present. It tells you how much of the element happens to be in the one specific condition required to make that line, at the temperature and pressure of that particular star. Saha worked out the principle. Two physicists in England, Ralph Fowler and Edward Arthur Milne, sharpened it into a tool astronomers could actually point at a spectrum, refining the method over 1923 and 1924. And Cecilia Payne, sitting at Harvard with the largest spectral archive in existence and a freshly minted understanding of this exact physics, was perhaps the single best positioned person on the planet to apply it. She had met Saha, she had absorbed Fowler and Milne, she had the plates, and she had the one thing the established men of the field did not have, which was no investment whatsoever in the answer coming out the way everyone expected. Now watch what the new physics does to the old assumption. Because this is the moment the lie comes apart in her hands. Take hydrogen. The famous dark lines of hydrogen in a star's spectrum, the Balmer lines, the ones in the visible part of the rainbow that astronomers had been staring at for half a century, are produced only by hydrogen atoms whose electron is already sitting in the second energy level, the first excited state, ready to jump up when it absorbs the right color. A hydrogen atom in its ground state, with its electron in the lowest level, does not produce these visible lines at all. It absorbs in the ultraviolet, where the instruments of the time could not see. So the visible hydrogen lines are made only by the small minority of hydrogen atoms that have been kicked up into that second level. And how small is that minority? In the atmosphere of a star like the Sun, at a temperature of around 5,700 Kelvin, the fraction of hydrogen atoms sitting in the second energy level, the only ones that can make the lines everyone was measuring, is roughly 1 in 200 million. Sit with that number. For every single hydrogen atom that is doing the absorbing, that is contributing to the dark lines astronomers were reading, there are 200 million hydrogen atoms standing right there in the same gas, invisible, contributing nothing to the visible spectrum at all. The line you see is the faint signal of a tiny fraction of the hydrogen. The overwhelming majority of it is hiding in plain sight, in a state the spectrum of the era simply could not register. The metals are a different story, and that is the cruelty of it. The lines of ionized iron and calcium and the rest, at the temperature of a sun-like star, are produced by a far larger fraction of those atoms, because their electrons sit in states that are much more easily reached at those temperatures. So a relatively small amount of iron, with a large fraction of its atoms in line-producing condition, throws up a bold, dark, dramatic set of lines. And an enormous amount of hydrogen, with all but one part in 200 million sitting silent, throws up a modest one. The spectrum was not lying about which elements were there. It was lying, catastrophically, about how much of each there was. The metals were loud and scarce. The hydrogen was quiet and everywhere. The light, in other words, wears a disguise. A star does not show you what it is made of. It shows you what its temperature and pressure permit it to show you. And the relationship between the two is exactly the relationship that Saha's equation describes, and almost nobody had thought to run the calculation backward, to start from the line strengths and the physics, and ask what the actual abundances had to be. Cecilia Payne ran it backward, star after star, element after element. She took the strengths of the lines and the temperature of the star and the ionization physics, and she worked out how much of each element had to be present to produce what she was seeing. For most of the elements, the heavier ones, 15 or 18 of them, the answer came out broadly consistent with what you would find on Earth, give or take, which must have been reassuring. The relative proportions of the metals in the stars looked something like the relative proportions of the metals in the ground. The old picture held for that slice of the periodic table. And then she got to hydrogen and helium, and the numbers detonated. Hydrogen did not come out as one element among many. It came out as roughly 1,000,000 times more abundant than the metals. Helium came out something like 1,000 times more abundant than the metals. Not more abundant, 1,000,000 times more abundant. The two simplest elements in existence were not part of the mixture. They were the mixture. Everything else was a contaminant floating in an ocean of the two lightest gases, and the ocean was so much larger than the contaminant that the comparison stops making intuitive sense. If the metals are a teaspoon, the hydrogen is a swimming pool, and that understates it by orders of magnitude. She did most of this work in a compressed burst that she later described, with the understatement of someone who knew exactly what she had done, as a period of about 6 weeks of something close to ecstasy. She was 24 years old. She was working through the physics and the data at a pace that her colleagues found difficult to keep up with, and she was watching the composition of the universe resolve itself in front of her, the real composition, the one no one had seen, and she knew. You do not write the way she wrote. You do not push the calculation as hard as she pushed it, unless some part of you knows that you are the first human being in history to see this particular thing clearly. And here is what I want you to hold on to, because it is the spine of the whole story. She was not speculating. This was not a clever hunch or a philosophical argument. This was a quantitative result, derived from the best data in the world, using the newest and most rigorous physics available. And it said, without ambiguity, that the universe is overwhelmingly hydrogen and helium. A thing that the entire field had declared, on the basis of the same data, read less carefully, to be false. A thing that the Dean of American Astronomers had personally locked into place a decade earlier with his beautiful, persuasive, wrong comparison between the Sun and the Earth. So she had in front of her a confirmed impossibility. Not impossible in the sense of being unsupported, impossible in the sense that it could not be true and also leave the existing consensus standing. One of them had to fall. Either the entire field was wrong about the composition of the cosmos, or a 24-year-old woman with no degree from her own country and a $500 stipend had made a mistake. You already know which way the institution was going to lean. But, I have skipped past the single most elegant piece of her demonstration, and I do not want to. Because it is the part that should have ended the argument before it started, and it is the part that shows how completely the field had been misreading the sky. It has to do with the classification system that Annie Jump Cannon had built, the sequence of letters O, B, A, F, G, K, M, that sorted the stars by the look of their spectra. Nobody, when that sequence was created, fully understood what it meant. It was an ordering by appearance, a filing system, the stars arranged by which lines were strong and which were weak. What Cecilia Payne showed, using Saha's physics, is that the entire sequence is nothing but a temperature sequence. It is the stars sorted from hottest to coolest. And every difference in the appearance of their spectra, every shift in which lines dominate, is the direct consequence of temperature acting on the same underlying mixture of elements through the ionization physics. The sequence everyone had been treating as a catalogue of different kinds of stars made of different things was a thermometer. Here is the proof, and I want to walk through it the way she would have seen it, because the detail is the content. Take the visible hydrogen lines, the Balmer lines, the ones at the center of the whole composition argument. If line strength meant abundance, the way everyone assumed, then the strength of the hydrogen lines should track how much hydrogen a star contains, and there would be no particular reason for it to do anything dramatic as you moved along Cannon's sequence. That is what you would expect. That is not what the plates show. What the plates show is that the hydrogen Balmer lines are weak in the very hottest stars, the O and B types, then grow stronger and stronger as you move to cooler stars, reach their absolute maximum strength in the A-type stars at a temperature of roughly 10,000 Kelvin, and then fade away again as you continue into the cooler F, G, K, and M stars. The hydrogen lines peak in the middle of the temperature range and weaken in both directions, toward the hot end and toward the cool end alike. Now sit with what that means, because it is decisive. If the strength of the hydrogen lines were telling you how much hydrogen was present, you would have to believe that the A-type stars are somehow rich in hydrogen, while the hotter stars and the cooler stars are both poor in it, which is a bizarre and arbitrary thing to believe, a hump in hydrogen abundance sitting in the middle of the temperature scale for no reason anyone could give. But Saha's equation explains the hump exactly, with no arbitrariness at all. In the hottest stars, the gas is so hot that the hydrogen is largely ionized, the electrons stripped clean away, so there are very few intact atoms left to produce the lines, and the lines are weak. In the coolest stars, the gas is too cold to lift enough electrons up into the second energy level, where the visible lines are produced, so again, the lines are weak. Only in the middle, around 10,000 Kelvin, is the temperature in the narrow band that keeps a healthy population of hydrogen atoms intact and excited into exactly the state that produces the Balmer lines. The peak is not a peak in how much hydrogen there is. It is a peak in how much of the hydrogen is in the one condition that makes the line. The abundance of hydrogen is essentially the same across all of them. What changes is the temperature, and the temperature changes what the same hydrogen is doing. She did this not just for hydrogen, but element after element, line after line, across the whole sequence, and every time the same thing happened. The wild apparent differences between the spectral classes dissolved into a single underlying composition seen at different temperatures. A hot star and a cool star look like utterly different objects in the spectrum, and they are made of nearly the same thing. The differences are a costume that temperature puts on a uniform mixture. That was the demonstration. The entire variety of the stellar zoo, the thing that had made the stars look like a menagerie of different substances, was the same gas at different temperatures, And once you understood the ionization physics, you could strip the costume off and read what was underneath. And what was underneath, every time, was overwhelmingly hydrogen. I find this almost unbearably elegant, and I also find it damning, because it means the answer was not hidden behind some inaccessible measurement that only later technology could reach. The plates were sitting in the building. Cannon's classification was sitting in the building. Saha's equation was 4 years old and freely published. Every piece was on the table by 1924, and what was required to assemble them was not a new instrument or a new observation, but a willingness to follow the physics to a conclusion the field did not want. Cecilia Payne supplied the willingness, the field supplied the resistance, and the resistance won the first round. But before we get to what they did to the result, I need you to understand that the result was not just correct. It was correct to a degree that when you see the modern numbers laid next to hers, is almost uncomfortable. We will get there. We will put her 1925 answer next to the best measurement of the sun's composition that exists today. The one from a team of astrophysicists in 2009, and you will see how little daylight there is between them. And when you see it, the thing she was about to be pressured into writing, the sentence about her own discovery being almost certainly not real, is going to read like one of the strangest documents in the history of science. A correct answer, signed by the person who found it, with a disclaimer attached saying she did not believe it. She had not written that sentence yet. In the autumn of 1924, she had the truth, and she knew it was the truth. What happened between that moment and the published thesis is the part of this story that the textbooks left out, and it is the part that should make you angry. The way the scientific establishment handled what Cecilia Payne found is not a story of a conspiracy, and I want to be precise about that, because the lazy version of this tale turns Henry Norris Russell into a moustache-twirling villain who stole a woman's work. And the truth is both more defensible and, in a way, more disturbing than that. Nobody locked her result in a vault. Nobody forbade her from publishing. What happened is subtler, and it is the kind of thing that happens constantly in every field to this day, which is precisely why it is worth slowing down to watch the mechanism work. Her thesis was going to be published. Shapley, to his credit, was supportive, and the work was going to come out as the very first volume in a new series of Harvard Observatory monographs, a real distinction. But before it went out, the manuscript was sent to Henry Norris Russell for his assessment, because Russell's opinion was the opinion that mattered, and because the result it contained directly contradicted Russell's own published conclusion from a decade earlier. So the person whose authority the discovery threatened was the person asked to bless it. Russell wrote back. The letter survives, recovered later from the Harvard archives by the historian Owen Gingerish, who had himself been Cecilia Payne's doctoral student, which is its own quiet loop in this story. And Russell's letter is not dismissive in the way you might expect. He calls the results striking. He says they appear remarkably consistent. He is, for most of the elements, impressed. And then he arrives at hydrogen and helium, and he plants his feet. He writes that there is one very much more serious discrepancy, that he is convinced something is seriously wrong with the present theory. And then comes the sentence that the whole story orbits around. He writes that it is clearly impossible that hydrogen should be 1,000,000 times more abundant than the metals. Clearly impossible. Not unlikely. Not in need of further checking. Clearly impossible. From the most powerful astronomer in the country, in writing to a 24-year-old with no degree and no standing about the central finding of her doctoral thesis. And the critique did not even come to her directly at first. It traveled the way authority tends to travel, from Russell to Shapley to Payne, down the chain of power, arriving as the considered verdict of the field rather than as one man's opinion that could be argued with on equal terms. Now, I have read the historians who push back on the dramatic telling, and they have a point worth taking seriously. The physics Cecilia Payne was using was, in 1925, genuinely new. Saha's ionization theory was barely 4 years old and far from universally accepted. A senior scientist looking at a radical result produced by a brand new and not yet trusted method, a result that overturned a decade of consensus, has a legitimate professional reason to urge caution. Extraordinary claims do warrant extra scrutiny, and David Dvorkin, who wrote the major biography of Russell, argues that Russell's skepticism was not simply a man defending his turf or a man dismissing a woman, but in part a reasonable scientific conservatism about an untested tool. That is a fair argument, and an honest reader has to hold it. But here is where I come down, and you can disagree with me, because this is the part where the evidence and the interpretation pull apart, and I am going to take a position rather than hide behind both hands. The caution was not applied evenly. The same new and untrusted physics produced her results for the metals, the ones that matched the existing picture, and nobody demanded she disown those. The method was only declared clearly impossible at the exact point where it contradicted Russell's own prior conclusion. A tool is treated as reliable when it confirms what the powerful man already believes, and unreliable when it does not. That is not the neutral application of scientific rigor. That is the way authority protects itself while telling itself a story about rigor. And the result, whatever the intentions behind it, was that a correct discovery got branded as impossible by the one voice loud enough to make the branding stick. So Cecilia Payne did the calculation that every junior person in every field eventually has to do, the calculation that has nothing to do with physics. She was 24. She had no degree from her own country, no faculty position, no power, and a future in astronomy that depended entirely on the goodwill of the very establishment that was telling her she was wrong. She could fight and lose and very possibly end her career before it began. Or she could find a form of words that let her survive, while keeping the result on the page where, if she was right, history would eventually find it. She chose the words. In the published thesis, after presenting the enormous abundances of hydrogen and helium, after laying out every number, she added the sentence. She wrote that the enormous abundance derived for these elements in the stellar atmosphere is almost certainly not real. In an earlier passage, she described the hydrogen and helium values as essentially spurious. She did not delete the result. She did not bury it. She left every calculation intact and visible, and then she stood over her own correct answer and publicly called it false. Dvorkin reads this, and I think he is right, as a deliberate and rather brilliant act of self-preservation. She preserved the result for posterity, recorded clearly that she was the first to find it, and simultaneously gave Russell and the establishment the deference they required, betting that if she was right, the vindication would come and the record would show she had been first. She was not a passive victim being silenced. She was a young scientist making a cold, clear-eyed political calculation about how to get the truth onto the permanent record while keeping her career alive, which is, when you think about what it actually required, a more impressive and a more damning thing than simple coercion. She had to be smart enough not just to discover the composition of the universe, but to navigate the precise amount of public self-betrayal that would let the discovery survive. That is the cost. That is what it took. A correct answer about the nature of all visible matter, signed by the woman who found it, carrying a disclaimer she did not believe. because the alternative was professional erasure. And the people who should be telling you this story, the ones who teach the composition of the stars as a settled and uncontroversial fact, mostly do not mention that the person who found it was made to disown it. This was published, recorded, and then quietly smoothed over until the smoothing became the official version. And it is worth pausing on what the smoothing cost her in the years that followed, because the disowned sentence was not the end of it. It was the beginning of a working life spent doing first-rate science from inside a cage the institution built and refused to acknowledge building. She got her doctorate in 1925, the degree formally granted by Radcliffe College, because Harvard, like Cambridge before it, did not grant doctorates to women, so even her landmark thesis came with an institutional asterisk. Otto Struve, one of the most eminent astronomers of the century, would later call that thesis the most brilliant doctoral thesis ever written in astronomy. The most brilliant ever written, and the institution that received it would spend the next 3 decades declining to treat its author as a full member of the profession. For years she was carried on the books not as an astronomer, but as a technical assistant to Shapley. Her salary, for a long stretch, was paid not out of any faculty budget, but effectively out of the observatory's equipment funds, which is to say the institution accounted for one of the great astrophysicists of the age as a piece of laboratory overhead, somewhere in the ledger near the photographic supplies. The courses she taught at Harvard were, for years, not even listed in the university catalogue under her name, so that students could take her classes without the record showing that a woman was teaching them. And the man who was president of Harvard for much of this period, A. Lawrence Lowell, is reported, in Donovan Moore's biography of her, to have told Shapley flatly that Cecilia Payne would never have a position at the university as long as he was alive. Not that she was not qualified, that she would never have the position, full stop, as a matter of his personal will. I want to stop here and make sure the weight of this lands properly, because it is easy to let it slide past as one more story of historical sexism, and it is that, but it is also something more specific and more useful to see clearly. The institution was not failing to recognize her ability. It recognized her ability perfectly well. It used her ability, taught from it, built on it, published it. What it refused to do was attach her name and her standing to the thing it was using. It wanted the discovery without the discoverer. It wanted the labor without the colleague. That is a different and more deliberate failure than mere blindness, and it is the same failure that had been worked on Annie Jump Cannon down the hall, and the same failure in its essence. That produced the disowned sentence in the thesis. The pattern is the same pattern every time. The work is welcome. The person is a problem to be managed. And now I am going to give you the thing I planted earlier, because we have reached the point in the story where the second layer of it has to open. And it is the layer that turns this from a story about one woman's mistreatment into a story about you. Remember what she actually found, not the politics of it, the content of it. She found that the universe is 2 gases, hydrogen and helium, and that everything else, the entire remaining periodic table, exists as a trace impurity amounting to no more than 1% or 2% of all the ordinary matter there is. Carbon, oxygen, nitrogen, calcium, iron, the complete inventory of every element that it is possible to build a planet out of, or a cell, or a memory. All of it, together, is the rounding error, and you are built entirely out of the rounding error. There is essentially no hydrogen and helium version of a human being. A person is made of the contaminant, the part the universe barely bothered with, the 1 or 2% of leftover that the 2 great gases did not account for. We are going to follow that all the way down before the end, because it gets worse, much worse. in a way that has to do with where the contaminant came from. But I want it sitting in your mind now, while we are still in the middle of the human story, so that when we arrive at the bottom of it, you will recognize that you have been walking toward this the whole time. The woman who was made to call her discovery false discovered, specifically, that you are made of the part of the universe that almost is not there. For now, though, the question in front of us is narrower and just as troubling. She had buried the truth alive in her own thesis, with a stone rolled over it that said almost certainly not real. The obvious question is how long it stayed buried, and who eventually moved the stone. And the answer to that is the part of the story that turns the quiet outrage into something sharper, because the stone was moved within 4 years, by the very man who had insisted it be put there in the first place. And when he moved it, he did not free her name. He put his own on top. In 1929, 4 years after telling Cecilia Payne that a hydrogen-rich universe was clearly impossible, Henry Norris Russell published a long and careful paper in the Astrophysical Journal titled On the Composition of the Sun's Atmosphere. It ran to more than 70 pages. In it, using his own methods, his own analysis of line intensities, his own data from Mount Wilson, he worked out the abundances of the elements in the Sun, and he arrived at the conclusion that the Sun is overwhelmingly hydrogen, the same conclusion Cecilia Payne had reached in 1925, the conclusion he had personally branded impossible. He had come around. The evidence, accumulating from several directions by the end of the 1920s, had become hard for even him to deny, and the Dean of American Astronomers reversed himself and declared that the universe was made of hydrogen after all. Now, to his credit, and I want to be fair, because the fairness makes the unfairness clearer, Russell did mention her. Near the end of that 70-page paper, he acknowledged that the most important previous determination of the abundances by astrophysical means was the one by Miss Payne, who had found the relative abundances of 18 of the most important elements. It is there. It is a real citation. He did not pretend she had never existed. But read where it sits and how it is framed. It is a brief acknowledgement of a prior determination, tucked toward the end of a paper presenting his own comprehensive results, in a structure that positions his 1929 analysis as the definitive word and her 1925 thesis as a useful precursor. He did not write that she had found the answer 4 years earlier and been pressured into disowning it, partly by him. He did not mention his own letter calling it impossible. He simply confirmed the result, credited her in passing, and let the weight of his authority settle the matter. And the weight of his authority is exactly the point, because it is what made the difference, and it is what made the theft, if you want to use that word, almost invisible. Dvorkin, who is careful and not given to drama, makes the observation that lands hardest for me. He notes that Russell's real contribution was not finding the answer. The answer had been found. His contribution was that his stature was large enough to convince the field that a radical conclusion was in fact real. In other words, the same authority that had been used in 1925 to suppress the discovery was used in 1929 to ratify it. And because ratification came from the top, the field absorbed the result as Russell's achievement. The truth needed the powerful man's permission to become accepted, and once it had his permission, it acquired his name. You can watch this happen in the citation record, which is its own kind of autopsy. By the middle of the 1960s, Russell's 1929 paper had been cited more than 3 times as often as Payne's 1925 thesis. For decades, the textbooks and the histories attached the discovery of the Sun's hydrogen composition to Russell. Generations of astronomers learned it as his, and the woman who had found it first, who had the result in hand 4 years before him, who had been told by him that it was impossible, became a footnote in the telling of her own discovery, if she appeared at all. This was the most important finding about the makeup of the universe in the 20th century, and the public record quietly assigned it to the senior man, and almost no one noticed, and almost no one objected, because the smoothing was complete and it looked exactly like the normal operation of science. I want to name the pattern directly, because naming it is the only thing that breaks its disguise. A junior figure, an outsider, often a woman, finds something true and uncomfortable. The establishment, through its most authoritative voice, declares it impossible, or improbable, or premature. The junior figure, lacking power, hedges or retreats. Time passes. The establishment quietly comes around to the truth, on its own schedule, through its own anointed channels, and credits its own. And the original discoverer is left holding a priority that the official history does not bother to honor. It is not a conspiracy. No one needs to coordinate it. It emerges naturally from the way authority and career and reputation are organized, and it has happened so many times that you could build a second periodic table out of the names. It happened to Payne. The same structure, in different keys, would echo through the century. The correct outsider silenced or sidelined, while the credit flowed upward to the people the system was already prepared to believe. And I want to count, because counting is the only thing that turns a sad story into evidence of a system. Lise Meitner worked out the theory of nuclear fission and explained the experiment that demonstrated it, and the 1944 Nobel Prize for the discovery went to Otto Hahn alone, her name left off entirely. Rosalind Franklin produced the X-ray image and the measurements that made the structure of dinar solvable, and the 1962 Nobel went to 3 men, one of whom had been shown her data without her knowledge. Shen Shengwu designed and ran the experiment that overturned a symmetry physicists had assumed was a law, and the 1957 Nobel went to the 2 theorists who predicted the result, not to the woman who proved it in the lab. Jocelyn Bell, as a graduate student, found the first pulsar in her own data, and the 1974 Nobel for the discovery went to her supervisor while she received nothing. That is 4, in physics and chemistry alone, in the same century, and I did not have to strain to find them, and the list does not end at 4. There is a pattern here, and the pattern has nothing to do with the quality of the work, because in every one of those cases, the work was not merely good. It was the kind of foundational work that prizes exist to honor. The pattern has to do with who the system was prepared to see as the author of a discovery, and who it was prepared to see as the instrument that produced it. Payne stands near the head of that sequence, an early and almost pure instance of a structure that would repeat with such regularity afterward that you could nearly set a clock by it. And the structure is not a row of individual villains you could name and condemn. It is a machine. The machine ran on her in 1925, and then it kept running, on woman after woman, for the rest of the century. And the fuel it ran on was always the same, a correct result produced by someone the system had already decided was not the kind of person from whom correct results are supposed to come. And here is the line I keep coming back to, the one that the careful historians and the dramatic popularizers actually agree on, even when they disagree about Russell's heart. The reason you have never heard her name is not that she was wrong, she was right. She was right earlier, and more directly, and with a clearer method than the man who got the credit. The reason you have never heard her name is that being right, by itself, has never been enough, and the people who run the institutions of knowledge have always been more comfortable receiving the truth from the people they already trusted than from the people they did not. So what happened to her? That is the question that decides whether this is a tragedy or something more complicated. And the honest answer is that it is more complicated. And the complication is the most interesting part of her, because she did not break. she stayed at Harvard. She kept working on variable stars, on the structure of the galaxy, on enormous patient surveys of stellar brightness, producing a body of observational work that ran to millions of measurements and stands on its own entirely, apart from the famous thesis. In 1934, she married a Russian-born astronomer named Sergei Gaposchkin, and the circumstances of that are worth a sentence. Because she had met him in Germany, and Sergei was effectively stateless, a man in real danger as the Nazi regime tightened, and Cecilia worked to get him out and to the United States, where they married and where she, the more established of the two, anchored both their careers. They had 3 children. She hyphenated her name to Payne Gaposchkin and carried on, doing the work, raising the family, teaching the students whose enrollment in her classes the catalogue declined to record. And slowly, far too slowly, the recognition that the institution had withheld began, grudgingly, to arrive. In 1956, more than 30 years after the thesis, Harvard finally appointed her a full professor. The New York Times reported it, noting that she was the first woman to reach a full professorship at Harvard through the ordinary process of faculty promotion. That same year, she became the chair of the Harvard Astronomy Department, the first woman to chair any department in that faculty. 30 years after she calculated the composition of the universe. The university that had paid her out of the equipment budget and kept her name out of the catalogue allowed her to become, formally, what she had been in substance since she was 24. There is one more piece of recognition that I find almost too perfect to be real. And it is real. And it is the kind of irony that the framework I have been using to think about this story would call structural rather than accidental. In 1976, near the end of her life, the American Astronomical Society awarded Cecilia Payne Gaposchkin its most prestigious honor for a lifetime of work, the Henry Norris Russell Lectureship. The prize named after the man who had told her, 50 years earlier, that her discovery was impossible, and who had then published it under his own authority. She accepted a Lifetime Achievement Award named for the person most responsible for the fact that her achievement had gone uncredited. I do not know how she felt standing there. I have read her words from around that time, and she was, characteristically, more generous and more philosophical about all of it than I think I could have managed. She talked about the reward of the young scientist being the thrill of being the first person in the history of the world to understand something, and the reward of the old scientist being the experience of watching a vague sketch grow over a lifetime into a finished landscape. She described her own career, looking back, as plodding on toward an unexpected goal, rewarded by the beauty of the scenery. She did not, in public, dwell on the bitterness, whether that is grace or whether it is one more accommodation forced on her by a lifetime of having to manage how she was perceived. I genuinely cannot tell you, and I have thought about it more than is probably reasonable. She died on the 7th of December, 1979, of lung cancer. By then the record had begun, slowly, to correct itself. Her own former student, Owen Gingerich, was among those who dug up the archives and made sure the real sequence of events was on paper. In the years since, and especially in the last couple of decades, her name has been steadily resurfacing, the citations of her thesis climbing as historians and astronomers go back and look at what actually happened. 100 years after the thesis, you are more likely to hear her name now than at any point in the century since she wrote it. The correction is real. It is also 100 years late, and it cannot reach her. But the recognition, even now, even corrected, tends to stop at the human level. It tends to be a story about a wronged woman finally getting her due, which is true and which matters. And it almost always stops there, at the biography, at the injustice, as if the injustice were the whole point. It is not the whole point. The injustice is the door. What is on the other side of the door is the thing she actually found, and what it means, and we have been circling it this entire time. Because the content of her discovery, followed all the way down, does not leave you with a feeling about a person. It leaves you with a feeling about yourself, and about the matter you are made of, and about how it got here. And that feeling is considerably harder to live with than the story of one stolen credit. She found that the universe is two gases. We have established that. What we have not yet established is the question that should have been keeping you up since I first mentioned the rounding error, which is, if the universe is hydrogen and helium, where did the rest of it come from? Where did the contaminant come from? Where did the carbon in your cells and the oxygen in your blood and the iron in your veins, the entire 1 or 2% that is everything that has ever mattered to anyone, where did all of that come from if the cosmos started as nothing but the two lightest gases? That question is the flaw of this story dropping out. And the answer is the most unsettling part of everything Cecilia Payne set in motion. Start with how right she was, because we owe her that before we follow the implication down, and because the precision is part of what makes the implication impossible to wave away. In 2009, a team of astrophysicists, led by Martin Asplund, published what became the standard modern reference for the chemical composition of the Sun, a painstaking analysis using three-dimensional models of the solar atmosphere and decades of accumulated spectroscopy that Cecilia Payne could only have dreamed of. Their numbers, the ones working astronomers reach for today, are these. The Sun is about 73.8% hydrogen by mass, about 24.9% helium, and everything else, the entire rest of the periodic table combined, the metals as astronomers loosely call anything heavier than helium, comes to about 1.3%, roughly 3/4 hydrogen, roughly 1/4 helium, and a sliver of everything else that rounds, depending on exactly how you measure it, to 1 or 2%. That is the answer Cecilia Payne wrote down in 1925. Hydrogen, overwhelmingly dominant, helium next, the metals a trace. The best instruments and models of the 21st century applied to the same star confirm the thing a 24-year-old worked out from photographic plates a century ago and was told was clearly impossible. The disclaimer she was pressured into writing, the sentence calling her own result almost certainly not real, sits in that thesis like a wound. Because the result was as real as results get. There was nothing spurious about it. The only spurious thing in the entire episode was the consensus that forced her to apologize for being right. And the composition is not local to the Sun. Look out at the broader universe, at the matter strewn between the galaxies, at the great clouds of gas, and the same proportions hold. The ordinary matter of the cosmos, the stuff that is not the dark matter and dark energy we still do not understand, is about 3/4 hydrogen and about 1/4 helium by mass, with everything else a rounding error. This is not the recipe of the Sun. This is the recipe of the visible universe. Cecilia Payne did not find out what one star is made of. She found out what almost all the touchable matter in existence is made of. And the answer is the two simplest things there are, in almost the entire supply, with a faint contamination of everything else. So the question stands, and now we follow it, because this is where the flaw gives way. If the universe is essentially hydrogen and helium, where did the contaminant come from? Where did the carbon and the oxygen and the iron come from, given that they are not part of the basic recipe? Begin at the beginning with the hydrogen and helium themselves, because even those have an origin, and the origin is shocking in its brevity. In the first few minutes after the universe began, when the entire cosmos was a fireball dense and hot enough to fuse atomic nuclei. Protons and neutrons slammed together and built the lightest elements. This is what physicists call Big Bang nucleosynthesis, and the framework for it was laid out in 1948 in a famous paper by Ralph Alpher, Hans Bethe, and George Gamow. A paper whose author list Gamow arranged partly as a joke so that the names would read Alpha, Bethe, Gamow, like the first 3 letters of the Greek alphabet. In those first minutes, the universe forged its hydrogen and its helium, and almost nothing else. The window was brutally short. Within roughly 20 minutes, the universe had expanded and cooled too much for fusion to continue, and the cosmic kitchen shut down, leaving behind a universe that was about 3/4 hydrogen and 1/4 helium. Those proportions, set in the first 20 minutes of time, are the proportions Cecilia Payne measured in starlight billions of years later. The recipe of the cosmos was written before the universe was half an hour old. But notice what was not made in those first minutes. No carbon, no oxygen, no nitrogen, no iron, none of the elements you are made of. The early universe made the 2 lightest gases and then quit. And for a long stretch of cosmic history, the universe was exactly what Cecilia Payne's numbers describe, and nothing more. 2 gases and a void. If the story had ended there, the universe would be permanently incapable of producing a planet, a chemistry, a cell, or a thought. Hydrogen and helium do not make people. There is no version of you that can be built from the basic ingredients of the cosmos. So where did the rest come from? It came from the stars. This is the discovery that grew directly out of the ground Cecilia Payne broke, worked out over the following decades by physicists like Fred Hoyle and the team behind the great 1957 synthesis of how elements are built in stars. The paper, known by the initials of its authors, Burbidge, Fowler, and Hoyle, one of whom, Margaret Burbidge, was another brilliant woman who fought the same institutions for the same recognition through the same century. What they established is that the heavier elements, the entire contaminant, are manufactured inside stars, in their cores, by fusion. Over the course of a star's life, and especially in its death, a star spends most of its life fusing hydrogen into helium, which is where its energy comes from, which is why the sun shines, which is the thing that lets you stand outside on a warm day. But when a sufficiently massive star runs low on hydrogen in its core, it begins fusing helium into carbon, then carbon into heavier things. Oxygen, neon, silicon, the star builds in concentric shells in its dying core, a foundry that climbs the periodic table, fusing ever heavier elements as it exhausts the lighter fuel until it reaches iron. An iron is the end of the line, because fusing iron does not release energy, it consumes it. So when the core of a massive star turns to iron, the furnace that has been holding the star up against its own gravity falls silent, and the star collapses and detonates as a supernova, an explosion so violent that for a few weeks it can outshine an entire galaxy. In that explosion, and in the cataclysmic merging of the dead cores of stars, the elements heavier than iron are forged, the gold and the silver and the rest, and the entire inventory. Everything the star built across its life, and everything the explosion created in its death, is hurled out into space. I skipped over the hardest step in that whole chain, and it deserves a moment of its own, because it is the step on which your existence most precariously hangs. Making carbon inside a star should be close to impossible, and the reason is a problem of timing. To build carbon, a star fuses helium nuclei together, but you cannot get from helium to carbon in one move. You first fuse 2 helium nuclei into a nucleus of beryllium, specifically beryllium-8. And beryllium-8 is so unstable that it falls apart almost the instant it forms, in less than a 10,000th of a trillionth of a second. So to make carbon, a third helium nucleus has to slam into that beryllium during the vanishing flicker of time before it disintegrates. The window is so absurdly brief that the reaction should almost never happen. And yet the universe is full of carbon. And you are full of carbon. So plainly it does happen. And for a long time, nobody could explain how it happened often enough to account for all the carbon there is. Fred Hoyle solved it in 1953 by reasoning backward from his own existence, which is one of the strangest and most audacious pieces of inference in the history of physics. He reasoned that since carbon clearly does get made in large quantities, since he was standing there made partly of it, there had to be something that dramatically sped up that third collision, a precisely tuned resonance, an energy level in the carbon nucleus sitting at almost exactly the combined energy of the beryllium and the incoming helium, so that the reaction would proceed far faster than it otherwise could. He calculated where that energy level would have to be for carbon production to work, and then he went to the experimental physicists at Caltech and essentially told them to go look for a resonance in carbon at a specific energy, around 7.65 million electron volts above the nucleus's ground state. Because he had deduced from the existence of life that it had to be there. They looked. It was there, almost exactly where he said it would be. A nuclear energy level, predicted not from nuclear theory, but from the bare fact that the person predicting it was alive, confirmed in the laboratory to sit at the one value that lets the universe build the element that builds you. That resonance is tuned to a razor's edge. Shift it slightly, and the third helium collision no longer fires fast enough, and the universe makes almost no carbon, and there is no organic chemistry anywhere, no biology, no thought, no version of you, only the two great gases and a thin scatter of the lightest few elements. The entire kingdom of complexity, everything that the contaminant makes possible, balances on the precise placement of a single energy level in a single nucleus. Hoyle, who was a committed atheist and not a man given to mysticism, was unsettled enough by this to remark that a sensible look at the facts made it seem as if a super-intellect had been monkeying with the physics. I am not telling you that to push you toward any conclusion about design, because the honest position is that we do not know why the constants sit where they sit, and a universe with different constants simply would not contain anyone to be puzzled by them. I am telling you because of what it reveals about the thing Cecilia Payne first measured. Complexity is not just rare and expensive and temporary. It is contingent on knife-edge coincidences in the structure of matter itself, so fine that the man who discovered one of them found it disquieting. The two great gases are robust. They would exist in almost any universe. You are the part that hangs on the resonance. That is where the contaminant comes from. Every atom in your body heavier than the hydrogen, and you do contain a great deal of hydrogen, mostly bound up in the water you are largely made of, came out of a star. The carbon that forms the backbone of every molecule in you was fused in a stellar core. The oxygen you are breathing right now, the oxygen in the water in your cells, was made in the heart of a star and blown out into the galaxy when that star died. The calcium in your bones, the iron in your blood, the iron in the hemoglobin that is carrying oxygen through your arteries at this exact moment, was forged in the final convulsions of a massive star and scattered across space by a supernova before the Earth existed. You have heard some version of this phrased prettily as stardust, as we are made of star stuff, and the pretty phrasing has worn the strangeness smooth. So let me put it back the way Cecilia Payne's numbers actually leave it. The universe is two gases. You are not made of the universe. You are made of the exceptions to the universe, the trace impurity. the 1 or 2% that the cosmos manufactured almost as an afterthought, inside stars, and could only release by destroying those stars. Every heavy atom in you is a fragment of a dead star. Your body is an assembly of stellar corpses. The matter that thinks your thoughts and moves your hands was cooked in furnaces that had to explode for you to exist. And it spent billions of years drifting through the dark as debris before gravity gathered it into a planet and chemistry gathered it into you. You are not the universe contemplating itself, which is the comforting version. You are the universe's leftover ash, briefly arranged into a pattern that can ask where it came from, and the honest answer is that it came from things dying. I said this would get worse, and I want to make sure you feel the specific way in which it is worse, because it is not the cosmic loneliness, the smallness, the feeling tiny under the stars sensation that popular astronomy sells as wonder. It is more intimate than that. It is that the very thing that makes you possible, the existence of any element beyond the two basic gases, is a record of destruction. Complexity in this universe is not the default. The default is hydrogen and helium, simple and abundant and going nowhere. Everything interesting, everything that can be built into structure, into life, into a mind, is rare. And it is rare because it is expensive, and the currency it is bought with is the death of stars. You are not evidence that the universe tends toward you. You are evidence of how much had to be burned down to produce the small contaminated fraction in which something like you can briefly happen. And this is the third time I am bringing you to the edge of it, and it is the last time before we go over. So let it land. The woman who discovered what you are made of was made to call her discovery false. And what she discovered, underneath the politics, underneath the stolen credit, underneath the technical assistant's salary, and the catalogue that left her name out, was that you are made of the part of the universe that almost is not there, assembled from the wreckage of stars. An impurity so slight that the cosmos rounds it off to error. She found the truth about your substance, and she was forced to disown it, and the same century that forced her to disown it also taught itself, slowly, to look away from what the truth actually says about you. Both suppressions ran in parallel, the one done to her and the one done to the meaning of what she found. We are at the bottom now. There is one more layer, and it is the layer where her story and your substance stop being two separate things and become the same thing. And I have been walking you toward it since the first sentence. Before we go over the edge, I have to tell you that the truth Cecilia Payne found had to win twice, because the first victory was only about the surface of the stars, and the establishment fought the second battle just as hard. This is the part where the abdication of authority stops being a single episode and reveals itself as a habit, and it is worth seeing, because it tells you the suppression of her result was not a one-time failure of one man's nerve. Her thesis was about stellar atmospheres, the outer layers, the thin shell of gas where the light we see is produced. Even after Russell's 1929 paper made it respectable to say the sun's atmosphere was mostly hydrogen, a separate and equally entrenched assumption survived, which was that the inside of a star, the dense core, must be a different matter entirely, a heavy mixture more like a metal than a gas. And the man defending that assumption was Arthur Eddington, the same Eddington whose eclipse lecture had set the teenage Cecilia Payne on fire a decade earlier. Eddington had built the foundational theory of how stars hold themselves up and how they shine, and his models assumed stellar interiors were composed of heavier material. The idea that a star could be mostly hydrogen all the way down struck him, and many others, as physically implausible, and the argument over the composition of stellar interiors dragged on through the 1930s. Fred Hoyle, who would later do more than almost anyone to explain where the elements come from, was himself resistant for a time to a fully hydrogen-dominated picture of the deep interior. So the truth had to be established twice, once for the outside of the stars and again for the inside, and both times it had to overcome the considered judgment of the most authoritative figures in the field. And both times the figures were not stupid or malicious, but simply heavily invested in the framework they had built their careers inside. This is the thing I keep wanting you to see clearly. The resistance was not an aberration. It was the normal immune response of an institution to a truth that did not fit, and it operated through the most respected people in the room, and it lost only slowly, only as the evidence became overwhelming and the holdouts died or relented. The composition of the universe, the single most basic fact about the matter of existence, was not handed gratefully to the person who found it. It was extracted from the field one grudging concession at a time, over decades, against the active resistance of the people who should have been most eager to know. And I want to be honest with you about something, because the framework I am using to tell this story has a built-in temptation toward making every establishment figure a coward and every outsider a martyr, and the truth is messier, and I respect you too much to sand it down. Eddington was a great scientist. Russell was a great scientist. Hoyle was a great scientist. Their resistance was not contemptible. It was, in each case, the application of hard-won judgment to a claim that genuinely strained that judgment. The problem is not that they doubted. Doubt is the job. The problem is what their doubt was allowed to cost a person who had less power than they did, and the asymmetry of who pays when the powerful are wrong. When Eddington doubted the hydrogen interior, nothing happened to Eddington. When Russell doubted the hydrogen atmosphere, the cost was paid by a 24-year-old who had to print a lie about her own work to survive his doubt. That is the part that does not come out in the wash. Being wrong for the powerful is free. Being right for the powerless can cost everything, and frequently does. Now let me show you why the thing she found is not a distant fact about distant objects, but the reason you are conscious to hear this at all, because the scale of the connection is the part that the textbook version flattens into nothing. The sun shines because it is mostly hydrogen. That is not a casual statement. The sun's energy comes from fusing hydrogen nuclei into helium in its core, and the rate at which it does this is staggering in a way the numbers barely contain. In every single second, the sun fuses roughly 600 million tons of hydrogen, converting a few million tons of that mass directly into energy, pouring it out as light and heat in every direction. It has been doing this for about 4.5 billion years, and it has enough hydrogen to keep doing it for billions more. The reason the sun has a fuel supply large enough to run for 10 billion years, the reason it did not burn out long before life could arise on Earth, is precisely the thing Cecilia Payne discovered and was told was impossible. The sun is mostly hydrogen. If the old consensus had been right, if the sun were a heavy mixture of metals like the Earth's crust, it could not work the way it works, could not last the way it lasts, could not have held steady long enough for anything like you to evolve under it. Follow the chain. The sun is mostly hydrogen, so the sun shines steadily for billions of years. That steady light falls on the Earth, and plants capture it and turn carbon dioxide and water into the sugars that are the base of nearly every food chain on the planet. Every calorie you have ever eaten traces back, through some number of steps, to a plant capturing the light of a hydrogen fire. The oxygen you are breathing was released by those same plants splitting water with that same light. The warmth that keeps the planet in the narrow band of temperature where liquid water exists, and where chemistry can be complex enough to build a living thing, comes from the same hydrogen fusion. You are alive, right now, in every breath and every heartbeat. Because the universe is mostly hydrogen, and because one particular ball of it has been quietly fusing for long enough. The fact a 24-year-old extracted from photographic plates in a basement and was pressured into disowning is the fact underwriting your continued existence between one sentence of this and the next. And here is the irony I cannot stop turning over, the one that the structure of this story seems almost to have arranged on purpose. Cecilia Payne discovered that the interesting matter, the matter that can build complexity and structure and life, is the rare contaminant, the trace exception that the universe produces only by exception and at great cost. And she herself was exactly that, inside her field. A woman in early 20th century astronomy was the contaminant, the trace exception, the thing the institution was built almost entirely without, the impurity in a system that was, by overwhelming proportion, men, and that treated the rare exception the way the universe treats the heavy elements, as something to be used in small quantities and otherwise rounded off to error. She found that all the structure worth having is made of the suppressed trace. And she lived it. The discovery and the discoverer were the same shape. The matter that matters is the matter the system has the least of and values the least. And that was true of the carbon in her cells, and it was true of her standing in her science. And I do not think she could have failed to feel the symmetry, though she was far too disciplined to say it out loud in those terms. The personal and the physical are not separate threads in this story. They are the same thread running in both directions. A woman treated as a negligible exception discovered that existence itself is built out of the negligible exceptions, and was then made negligible in the telling of it, and the negligibility she was forced into is the precise mirror of the truth she uncovered. You could not write it as fiction. It would seem too neat. And yet the dates and the documents are all there. The letter calling it impossible, the disowned sentence, the equipment budget salary, the prize named after the man who doubted her, and the 73.8% that proves she was right all along. But the universe is not done with the bad news, and neither am I, because there is a dimension to her discovery that becomes visible only when you stretch it across time. And it is the dimension that I think is genuinely hard to live with once you have seen it, harder than the smallness, harder than the stellar death, harder than the stolen credit. It is what the composition of the universe implies about the future. The universe began as hydrogen and helium. The contaminant, the heavy elements, the matter you are made of has been slowly built up over cosmic time inside stars. A little more with each generation of stars that lives and dies and seeds the next. So the fraction of the universe that is interesting, that is capable of complexity, has been very slowly rising since the beginning. But here is the thing about that process. It runs on hydrogen, and hydrogen is finite, and the universe is spending it. Every star that shines is converting hydrogen into helium and heavier things, and locking some of that material away forever in the dead remnants of stars, the white dwarfs and neutron stars and black holes that no longer return their matter to circulation. The supply of fresh hydrogen available to form new stars is, on the longest timescales, decreasing. The rate of star formation across the universe peaked billions of years ago and has been declining ever since. We are living, right now, in the long, slow afternoon of cosmic star formation, well past the peak on the downward slope. The lights are not going out tomorrow, or in a billion years, or in a trillion, but the direction is set. Over timescales that make the current age of the universe look like an eye blink, the stars will burn through the available hydrogen. The bright stars will die and not be replaced, and the universe will fade toward a cold, dark, dilute state of dead remnants and thinning gas. drifting apart in an accelerating expansion. The era of starlight, the era in which complexity is possible, in which there is enough energy flowing and enough heavy matter assembled to build a planet or a cell or a thought, is a chapter. It had a beginning. It will have an end. And on the scale of the universe's full lifespan, it is brief, which means the contaminant, the interesting matter, the stuff you are made of, is not just rare in space. It is rare in time. You exist in the narrow-lit window of cosmic history, the brief stretch after enough stars had died to make heavy elements, and before the hydrogen runs low enough that the lights begin to fail. The universe was simple at the start, 2 gases and nothing else. And it will be simple again at the end, cold remnants and dark. And in between, there is a passing flush of complexity, a temporary contamination of the great simplicity, and everything that has ever happened, every life, every thought, every love, every discovery, including Cecilia Payne sitting in a basement working out the composition of the stars, including you listening to this, happens inside that flush, that brief deviation from the hydrogen and helium, default that the universe began with and will return to. She found the recipe of the cosmos, and the recipe, read all the way to its conclusion, says that the cosmos is overwhelmingly, almost entirely, the simple and the empty, and that the complexity is the exception in space and in time, the trace impurity in a vast simplicity, expensive, temporary, and bought with destruction. That is the full shape of what she discovered. Not a fun fact about stars being made of gas, a statement about how thin and how brief and how purchased the realm of interesting things actually is, and she was made to sign her name to it, and then write underneath it that she did not believe it. We are over the edge now. There is nothing left to set up. There is only the thing itself, and the woman, and the sentence, and what it leaves you holding. I want to do one more thing before the end, because I have been arguing a position throughout this, and I owe it to you to show you where even the people who would argue against me end up, since that is where the real weight is. There are, broadly, 2 ways the history of science tells this story. There is the dramatic version, the one you find in the magazine pieces and the celebratory threads, which says that Cecilia Payne discovered the composition of the universe, was forced by a powerful man to recant, and then watched that same man steal her credit. And there is the careful version, the one the serious historians like David Dvorkin construct from the actual archives, which complicates almost every beat. It says Russell's skepticism was partly legitimate, given how new the physics was. It says she was not literally forced to recant, but made a shrewd political choice to hedge while preserving her priority. It says Russell did cite her, that the credit dynamics were messier than theft, that the word forced does more work than the documents strictly support. I have given you both as honestly as I can, because you are not a child, and you do not need the story flattened into a hero and a villain to feel its force. But now watch what happens when you set the 2 versions side by side and look for what they share, because the shared part is the part that should keep you up. The dramatic version and the careful version disagree about Russell's motives. They disagree about how much pressure there was and what kind. They disagree about whether to use the word forced or the word chose. They do not disagree at all about the 2 facts that actually matter. She was right, and she was made, by one mechanism or another, gentle or harsh, malicious or innocent, to write in her own thesis that she was wrong. Every account agrees on that. The defenders of Russell agree on it. The critics of Russell agree on it. The most cautious historian and the most breathless popularizer agree on it. The disagreement is entirely about whom to blame and how angry to be. The fact itself, the correct discovery, carrying a disclaimer of disbelief signed by the discoverer, is not in dispute in any version of the story anyone tells. And that is the thing I cannot get past. We are not arguing about whether it happened. We are only arguing about how to feel about it. The event is settled. The only open question is the size of the outrage, and the field has spent a century preferring the smaller number. So let me ask the question that this opens, the one that I think is the actual reason a story this old still matters, the reason it is not just a biography. How much of what you have been taught as settled, neutral, uncontroversial fact arrived in your head, having passed through a moment like that one? How many of the clean sentences in the textbooks, the ones presented as the calm accumulation of knowledge, are smoothed over versions of something that was found by a person who was made to doubt it, or doubted into silence, or credited to someone else once it became safe to believe? We do not, as a rule, record the disowned sentences. We record the result and the eventual consensus, and we file away the cost of getting there, the letters calling it impossible, the careers paid out of the equipment budget, the names left off the catalogue. The official version of how we know things is itself a sanitized version. And the sanitizing is not usually a lie exactly. It is an omission. It is the same omission, scaled up across the entire enterprise, that kept Cecilia Payne's name off her own discovery for 50 years. This is the part the Fault Lines audience already suspects, and I am not going to pretend the suspicion is paranoid, because in this case it is simply correct. The version of scientific history you were handed is the press release. It is the part that was comfortable to say out loud. The thing scientists know privately, the thing the archives hold, the thing the careful historians have to dig for, is that the road to even the most basic facts ran through rooms full of power and fear and self-interest, and that the people who paid for the facts were very often not the people whose names ended up on them. That is not a conspiracy. Nobody coordinated it. It is worse than a conspiracy in a way, because a conspiracy could be exposed and dismantled, and this cannot, because it is just the shape of how institutions metabolize uncomfortable truth. They take it in slowly, through the channels they trust, and they round off the people they do not. I keep coming back to her own words from late in her life, because they are not the words of a bitter woman, and that itself is the most unsettling thing about them. She wrote, looking back, about the particular joy of science being the joy of coming upon a fact that cannot be understood in terms of the currently accepted ideas. Sit with that for a second, in light of everything you now know. The thing she named as the deepest joy of the work, finding the fact that does not fit, was the exact thing that nearly destroyed her. Because she found the fact that did not fit, and the accepted ideas did not yield to it gracefully, they fought it, through her, at her expense. She knew. She had to have known. She named the joy and the wound in the same breath, and called it joy, and I do not know whether to read that as transcendence, or as the final, deepest accommodation. A woman who had been made to disown the truth once, declining, decades later, to disown her love of the work that had cost her so much. I have gone back and forth on it for a long time, and I still cannot land. And there is a smaller line of hers that I held back from earlier, because it only lands now, at the end, with everything stacked behind it. Describing her whole career in retrospect, she said she had simply gone on plodding, rewarded by the beauty of the scenery, toward an unexpected goal. Plodding. The woman who worked out the composition of the universe in a 6-week fever at 24 called the rest of her life plodding. The most brilliant doctoral thesis ever written in astronomy, followed by 50 years of being told, in 100 small institutional ways, to keep her head down. And she absorbed it so completely that she narrated her own extraordinary life in the register of a person walking slowly through pleasant terrain. There is grace in that, and there is also the long shadow of a discipline imposed early and never fully lifted, and the two are so tangled in her voice that you cannot pull them apart. And I think that inability to pull them apart is the truest thing I can tell you about what was done to her. It went all the way in. It became the way she talked about herself. Her former student, Owen Gingerich, is the one who went into the Harvard archives and pulled out Russell's letter, the clearly impossible letter, and made sure the sequence was documented. Made sure that when the correction finally came, it would have the paper to stand on. There is something fitting about that. The student recovering the teacher's stolen priority, the next link in the chain reaching back to mend what the previous links had broken. The record is better now than it was. Donovan Moore wrote a full biography in 2020, titled with the question itself, what stars are made of, and put her at the center of it where she belongs. The citations of her thesis have climbed steeply in the last 20 years as the field circles back to look honestly at what happened. A century after she wrote it, the disowned sentence is finally being read the way it should always have been read, as the most courageous lie in the history of astronomy. A true thing dressed as a false one, so that it could survive long enough to be believed. But none of that reaches her. She died in 1979, with the correction barely begun, having spent her one life being right, and being made to say she was not. The vindication, real as it is happening over her grave, conducted by people she will never meet, about a truth she knew before any of them were born. And the universe she described, the one that is overwhelmingly two simple gases with a brief expensive contamination of everything that matters, does not register the correction at all, because the universe does not know her name and never did and was never going to, and that indifference is the last thing I have to hand you, because it is where the human story and the physics finally close into a single point. The matter does not care who measured it. The hydrogen does not know it was counted. The iron in your blood does not know which star it came from, or that a woman in a basement once worked out the proportion of it in the cosmos and was punished for the answer. The whole vast simple universe rolls on, spending its hydrogen, building and destroying its trace of complexity, indifferent to the small contaminated patterns that briefly arise inside it and ask what they are made of. She gave that indifferent universe an answer about itself. It did not thank her. The men who could have thanked her mostly did not either. And the answer remains true regardless, sitting in the spectrum of every star, waiting, the way it waited for her, for anyone with the nerve to read what the light is actually saying instead of what the consensus expects it to say. That is where I have to leave the people. Now there is only the thing itself. So here is what you are, stated as plainly as the physics allows, with nothing softened. You are mostly water, which means you are mostly hydrogen and oxygen. The hydrogen in that water is the oldest matter in your body by an almost unfathomable margin. It was made in the first 20 minutes after the universe began, in the cosmic fireball, before there was a single star anywhere. The hydrogen atoms in the water in your cells have been hydrogen for nearly 14 billion years. Unchanged, passed from the Big Bang through the void, into a cloud, into a planet, into a glass of water, into you, carrying their age silently the whole way. Part of you is as old as time. Part of you is the original substance, the great simple gas the universe started with, the same hydrogen Cecilia Payne found filling the stars. And the rest of you, the part that makes you more than water, the carbon and the nitrogen and the calcium and the iron, none of that is primordial. All of it was made later inside stars and could only be released by their deaths. The carbon in every protein in your body was fused in a stellar core. The oxygen bound into that primordial hydrogen to make your water was forged in a star and blown out in its death throes. The iron carrying oxygen through your blood right now, this second, was made in the final collapse of a massive star and scattered across space by an explosion that happened before the sun existed. So, you are not one thing. You are a seam. You are the place where the beginning of the universe and the death of stars meet and briefly hold a shape. The oldest matter there is, mixed with the ash of things that had to be destroyed, arranged for a little while into a pattern that can know it. That is not a metaphor, and it is not a poem. It is the direct, literal, measured consequence of the fact a 24-year-old extracted from photographic plates in 1925 and was told to call false. The universe is two simple gases. Everything that is not those two gases is rare and expensive and made by destruction and temporary. And you are made entirely of the everything that is not those two gases, plus a little of the ancient gas itself on loan. You are the trace. You are the contamination the cosmos produces by exception and reclaims by default. You are the part of the universe that almost is not there, that the great simplicity rounds off to error, briefly convinced that it is a person. And the window you are doing this in is closing. Not soon, not in any time scale that should frighten you tonight, but inevitably, set in the same proportions Payne measured. The hydrogen is being spent. The stars that make the heavy elements are forming more slowly than they used to and will eventually stop. The contamination will thin. The lights will go out one by one across timescales that dwarf everything, and the universe will settle back toward what it was at the start and what it tends toward by nature, cold and dark and simple, hydrogen and helium and the locked-away corpses of the stars that briefly made it interesting. The flush of complexity, the era in which a thing like you can exist and ask what it is made of, is a passing condition. It had a first star, and it will have a last one. You are living inside the lit part of a sentence the universe is slowly finishing. And the sentence ends in the same simplicity it began in, and everything that has ever mattered to anyone happens in the lit part, the brief contaminated middle, between two long stretches of the great gas going nowhere. Cecilia Payne found all of that, not the poetry of it, the numbers of it, the part that is true, whether or not anyone says it beautifully. She found what you are made of and where it came from, and how rare it is, and how briefly it gets to be arranged this way. And the field she gave it to told her it was impossible. And she wrote in her own thesis that her own discovery was almost certainly not real. And a more powerful man published it 4 years later and got the name on it for 50 years. And you grew up being able to say the stars are made of hydrogen without ever once being told who paid for that sentence or what it cost them to set it down. I think about the disowned line more than I think about almost anything else in the history of science. A young woman, alone in a country not her own, with no degree from her own country, and a salary filed under laboratory supplies, holding the correct answer to the oldest question about the sky, and being made to stand over it and write that it was not real. She did it to survive, and it worked. She survived, and the truth survived with her, buried alive in the one place she could be sure it would eventually be found, her own permanent record. She bet that being right would outlast being doubted. She was correct about that too. It took 50 years, and it came too late to reach her, but she was correct. She was always correct. That was never the question. The question was only ever whether the people with the power to decide what counts as real would let her be correct out loud. And the answer, for most of her life, was no. The number is 73.8% hydrogen, 24.9% helium, a little over 1% everything else. Everything that builds a world or a body or a thought, everything you are, everything she was. That is the composition of the sun, measured with instruments she never lived to see, and it is, to within a rounding error, exactly what she wrote down in 1925 and was told could not be true. She was right. She knew she was right. And she signed her name to a sentence saying she was wrong, so that the truth could outlive the people who refused to hear it. It outlived them. It will outlive us. It is sitting in the light of every star above you tonight, the same answer she read off the plates, waiting in plain sight, the way it was always waiting. For anyone willing to look at what the universe is actually made of, instead of what they were told it had to be. You are made of the part that almost is not there. The woman who found that out was made to call it a lie, and the stars have been confirming her ever since, in a light that does not know her name and never will.